the direct impulse function, its shifting property, and the impulse train. The direct delta, or direct impulse, cannot be concisely defined in the usual way. For example, this statement is true, but not sufficient to exactly describe delta of t, because nothing on the right side of the equality would change if we multiply the left side by a positive real constant. The direct impulse is a generalized function, whose definition is best stated in other ways. A better way to describe delta of t is by measuring its area. The limits of integration may be narrowed to an arbitrarily small region near t equals 0, and the area of delta of t stays at 1. This means that delta of t has area 1 that is concentrated at a single point in time. When graphing the direct impulse delta of t, we indicate its area 1 next to an arrow pointing up to infinity. Think of delta of t as having 0 width, infinite height, and unity area, located at the single point in time t equals 0. Area at a single point is difficult to visualize, so this example may help. Here is a rectangular pulse, which according to its definition has width 1 and height 1, and hence area 1. Let's cut its width in half and double its height, so that the area stays equal to 1. Again, cut width in half and double the height. When this operation is repeated an infinite number of times, we obtain a pulse whose width is 0 and height is infinity and whose area is equal to 1. We obtain the direct impulse function delta of t. The direct impulse may have area other than 1. This is achieved by multiplying it by some scaling factor. In fact, the area may even be negative, as with other functions. To understand how a direct impulse may have area a, where a is not equal to 1, repeat the previous example starting with a rect of t instead of rect of t. Returning to delta of t, note that it is located at the value of t that makes the argument of delta go to 0. Here, for example, the value t equal to 1 makes the argument t minus 1 go to 0, so the impulse is located at t equal to 1. And here, the value t equal minus 0.5 makes the argument t plus 0.5 go to 0, so the impulse is located at t equal minus 0.5 seconds. By subtracting a time offset from t in the argument, we achieve time shifting, which will soon be covered in another video. Note that, just as the area of a delta function is equal to 1, a time-shifted version of the delta function still has area 1. When measuring area over all time, time shifting has no effect. Here is a direct impulse, which we assume to have area 1 when not otherwise noted, time shifted to t equal t0. Multiply the impulse by some continuously varying function of time x of t. How does this multiplication affect delta of t minus t0? Well, the only value of x of t that matters is its value at the impulse location. The impulse area gets scaled by the value of x of t at t equal t0. In fact, we may replace x of t with a constant waveform c equal x of t0, and the product remains the same. That is stated here. X of t times delta t minus t0 is equal to x of t0 times delta minus t0. Since a time-shifted impulse has area 1, when multiplied by x of t0, its area is scaled by that constant to now be x of t0. Integrating the left side of the equation over all time to get its area, we know that area must equal the area found on the right. This gives us the shifting property of the direct impulse function, as it sifts out one of infinitely many amplitude values of x of t. It is also called a sampling property, because it extracts a sample of x of t at a particular time instant. Finally, let's consider a single delta of t, to which we add delta of t delayed by t seconds, to which we add delta of t delayed by 2 capital T seconds, to which we add delta of t delayed by 3 capital T seconds, etc., all the way to infinite time, and following the same pattern, all the way to negative infinite time. What we have is a series of direct impulses that are spaced by capital T seconds along the time scale for all time, such that one of these impulses lands exactly at t equals 0. We call this repeating train of impulses delta sub capital T of t, where capital T specifies their spacing in time. Here is a summation that describes this impulse train function that is also called the comb function. For example, this is a plot of an impulse train having period capital T equal 4.2 seconds. We will use the delta function and the impulse train extensively throughout the course. The delta function can be used to represent points of nonconvergence or as a tool for creating time delay or frequency shift. The impulse train is used both for sampling a signal and as a tool to model periodic signals. Fortunately, both the impulse and impulse train simplify calculations considerably when appearing inside of an integral expression due to the sifting property.